Hey y'all, in today's video, we are going to use rice tables to figure out changing equilibria systems. We're going to use the rice tables to figure out what new concentrations would be if there was a change to a system or a perturbation to a system that was already at equilibrium. So let's go ahead and get started. Let's start by reviewing rice tables. A rice table is a wonderful linearization of some difficult stoichiometry. We've used it in the past for limiting reactants, and now we're going to use them a lot in equilibrium. When we set up a rice table, we start with the reaction, then initial, change, and E historically has stood for end, but in equilibrium, we're going to put it as equilibrium. But in the end, it's still kind of the end. So when we set up a rice table, we need to think about our reaction that's balanced. The initial would be any initial values that we are given. This change represents the change in the values, and that's based off of the coefficients of our balanced reaction. So we've always used X in this case. So if the coefficient was 1 and it was a reactant, we'd say it's minus X because a reactant goes down. And it goes down by 1x because the coefficient of that reactant is 1. If the reactant coefficient was 2, we'd say it was minus 2x because the coefficient's value is 2, and it's a reactant, which means it's going to go down. Products, we do the opposite. If it's a coefficient of 1, it would be plus x, coefficient of 2, plus 2x. And at the end, at equilibrium, what we're doing is we're simply taking our initial and adding or subtracting the value of the change. So what we're going to do today is put these rice tables into action as it pertains to equilibrium. Here's where rice tables can vary in equilibrium, though. In stoichiometry, when we used rice tables, we always saw reactions as going from, well, left to right. And when a reaction goes from left to right, the reactants are always going down and the products are always going up. But in this case, with equilibrium, we're dealing with reversible reactions that can go in either direction, which means that the reactants or the products could be going up or down depending on our Q and our K. When we look at an equilibrium expression, remember it's products over reactants raised to the power of their coefficients. And we've used equilibrium constants to determine whether a reaction favors the forward or reverse direction overall. And then we've used Q and compared it to K to figure out if the reaction is going to go forward or reverse if you're not at equilibrium. Today, we're going to apply that in these rice tables. If Q is less than K, we are going to favor our forward direction. That means products are going up, positive change. Reactants are going down, negative change. If Q is greater than K, then the products are going to go down and the reactants are going to go up. So the products would be a negative X or 2X or whatever, and the reactants would be a positive X or 2X or whatever. There are many things that can cause a change in equilibrium position without changing the equilibrium constant. So an equilibrium constant is constant as long as the temperature is the same. As we start changing the temperature, we change the constant, but there are many things that will change the Q value. And in the last video, we talked about how to find Q values when we're not at equilibrium. Q values can change when you do things like dilute a solution or increase the volume of gases. You can also add or remove reactants or products. All of these things will change the Q value and cause the entire reaction to shift its equilibrium position. Unless you're changing the temperature, though, that equilibrium will always end up back at the same K value. So we're going to use these rice tables with that knowledge. And in this video, we're going to focus on changes that are not temperature dependent. So we're going to always be going back to the same K value in today's video. So there are a lot of things that can affect our equilibrium system here. And our job is to now figure out how to do the math associated with each of these changes. Let's take a look at our first problem. In our first practice problem, we're going to look at how changing the volume can affect our equilibrium position. I have here a reaction. It's already balanced. I'm given the K value for this reaction is 2. And I'm also given the equilibrium values for my gases A, B, and C. Now that's important. That means it's already at equilibrium. But here's the thing. If I cut the volume of that container in half, Immediately, I double all of those pressures. Remember, back to ideal gas law. Cut the volume in half, double the pressure. PV equals nRT. All right? When volume and pressure are on the same side, they are inversely related. So what I've immediately done is doubled the pressure. These are my new initials. My new initial values are now twice what my equilibrium values had been. And this is where Rice tables come in. So what I'm going to do is I'm going to write my equation, and under initial, I'm going to put 1 atmosphere for A, 2 atmospheres for B, and 2 atmospheres for C. Now I need to look at Q versus K to tell me which direction my reaction is going to shift. So if I solve for Q with these new values, 2 for B and C and 1 for A, my Q value is 4. 2 times 2 divided by 1. So my Q value is 4. 4 is greater than 2. That was my original K value. Because Q is greater than K, we shift towards our reactants. That means it's going to be change of A is plus X, and changes for B and C are going to both be minus X. Therefore, at equilibrium, A is going to equal 1 plus X, B and C are both going to equal 2 minus X. What I will then do, because I know the temperature didn't change, they go back to the same K value, 2, which means that my K value, 2, is equal to my equilibrium values, 2 minus X times 2 minus X divided by 1 plus X. I solve for X. One caveat to this is that the AP will not make you do quadratic equations. However, in order to solve this, you might need to do a quadratic equation. One thing to be aware of as it pertains to my class is I want you to be able to do quadratics. Even if I might not ask you to do it on an exam, or I might not ask you to do it on the AP exam, I still want you to be able to solve for this. So what you're going to do is use your quadratic equation to solve for the value of X. In this case, X could equal 2 different things. Once we do our quadratic equation, once we foiled everything and made sure that all the math is right, X could either equal 0.35 or 5.6. Now, it couldn't be 5.6 though. The reason is because you can't have a negative pressure. And 2 minus 5.6 would be negative, and so you can't do that. So the only reasonable answer here would be X equals 0.35. This means at equilibrium, A is equal to 1 plus 0.35. B and C would be equal to 2 minus 0.35. So at equilibrium, our pressures of A, B, and C would be 1.35, 1.65, and 1.65 respectively. In this practice problem, let's take a look at what doing a dilution would have as an effect on the equilibrium system. I'm given off the bat equilibrium values of my 3 different reactants. What happens if I do a dilution? In this case, I'm going to cut each of those concentrations by a factor of 3. So my new concentration of ammonia is 3 moles per liter. My new concentration of ammonium is 1 mole per liter. And my new concentration of hydroxide is 2 moles per liter. Now, by doing this dilution, we have affected our equilibrium. So I'm going to look for Q. When I plug these values in to find my Q, I realize that Q is going to be less than K. This means the entire reaction is going to shift to the right to reach its equilibrium again. This means that the concentration of ammonia is going to equal 3 minus X, and the concentration of the ammonium is going to be 1 plus X. The concentration of hydroxide is going to equal 2 plus X. Because we're going back to our original equilibrium constant, 2, we're going to go ahead and plug these in to our equilibrium expression. 2 equals the concentration of the NH4 plus times the concentration of OH minus divided by the concentration of NH3. Again, we're going to need to make sure we solve for X appropriately. We're going to use a quadratic to do that. And the only X value that makes sense here would be 0.702. So the X here is 0.702. Therefore, the concentration at equilibrium of NH3 is 3 minus 0.702. The concentration of NH4 plus is 1 plus 0.702. And the concentration of hydroxide is 2 plus 0.702. So again, to recap how we just did this, we first recognized that a change in our equilibrium system would cause a change in our Q value. The change in our Q value causes the entire system to shift. When the system shifts, it's dependent on whether Q is greater than K or Q is less than K. So we need to figure out what is Q, determine which direction it's going to shift. Once we do that, then we determine using a Rice table what those new equilibrium concentrations are going to be. So we've done it with gases, where we've changed the volume. We've done it with solutions, where we've changed the volume. Now let's take a look at another example. So here comes a complicated one. In this situation, we are going to first find the equilibrium concentrations, followed by a manipulation, a perturbation to my equilibrium, which changes the Q. So the first thing we need to do is find the equilibrium concentrations of my initial system. I'm giving you the K value and the initial concentrations of the NH3, the NH4 plus, and the OH minus. Now remember, I didn't give you directly the NH4 plus and the OH minus, but because I didn't give them to you, we're going to say they're 0. So the initial concentration of the NH3 is 0.5. Because of the fact that I don't have any products, I know that that goes down and the other two go up. So at equilibrium, that's going to be 0.5 minus X, and both of the products, the NH4 plus and OH minus, are going to be plus X each. I solve for X. When I solve for X, I end up with X equals 3 times 10 to the negative third. That means that at equilibrium, my initial equilibrium here, my concentration of NH4 plus and OH minus are both 3 times 10 to the negative third, and my concentration of NH3 is 0.5 minus 3 times 10 to the negative third, so 0.497. Now, once I figure that out, I'm going to perturbate the system. I'm going to change something. I'm adding hydroxide. And in order to do this, I'm going to focus on a couple of things. First of all, the system was already at equilibrium. I'm now changing that system so that it's no longer at equilibrium. By adding a product, I make my Q greater than K. This is going to shift the entire reaction to the left. And when it shifts to the left, my products are going to go down and my reactants are going to go up. And in fact, in this case, one thing that we need to be really careful of is the fact that the volume didn't change. I added 0.25 moles of my hydroxide without changing the volume at all. This makes my math much easier. So what I'm going to do is change the initial value for my hydroxide by adding 0.25 to it. So in this case, you'll see that I've added the 0.25 to my original amount of my hydroxide. Now, that amount is really small. So does the change of hydroxide really change it at all? Well, no. 0.25 plus 0.003 is 0.253. And if you're looking at sig figs, that 3 doesn't actually matter. So in a lot of cases, we'll ignore it. In a lot of cases, that 0.003 is inconsequential. In this case, I'll show it. Those are going to go down by a factor of X, by value of X. And as a result, we end up with a new equilibrium position, which is equal to, for the ammonia, NH3, 0.497 plus X. For the NH4 plus, 0.003 minus X. And for the OH minus, 0.253 or 0.25 minus X. When I solve for X in this case, my X value ends up equal to 2.9 times 10 to the negative third. So to find my new equilibrium values, what I'm going to do is add 2.9 times 10 to the negative third to my NH3, subtract it from my NH4 plus, and subtract it from my OH minus. So here I've used a Rice table to go from an equilibrium system through a perturbation back to a new equilibrium position. So that wraps up today's video. Let's recap. The key to this video was showing you how to use a Rice table to find new equilibrium values after a perturbation to your equilibrium system. The types of perturbations that we are going to focus on are things like changing volumes of gases or changing dilutions and concentrations of your aqueous solutions, adding reactants, adding products, removing reactants or removing products. And in each of these situations, it comes back to understanding how does the change affect your Q to figure out which direction your equilibrium is going to shift. Then using that understanding in a Rice table to find those new equilibrium values. Remember, as long as you're not changing the temperature, you're not changing the K value. You're just changing Q. You always end up back at the same K value as long as the temperature is the same. Today's video was written, directed, edited, and produced by Kevin Judd and Jessica Wang. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one.